Comencem? Sí, espera un minutet que això funcioni. Good morning, everybody. We are going to start now a series of seminars regarding the project Acroba that deals with the security of cyber-physical systems with application to microgrids. In this first talk that I will do myself, my name is Vicenç Puig. I'm part of the team of this project that is composed by Andreu Cecilia, Ramon Costa, and myself, and also Pol Baldoma that we'll present later. We'll introduce in the first talk an introduction about cyber-physical security from the automatic control perspective. After this talk, Andreu will introduce more advanced topics about watermarking using observers, and then Pol will introduce some more advanced research regarding attacks in complex systems. So I will introduce my talk. My talk, as I said at the very beginning, it is about the introduction about the security in cyber-physical systems. Just a minute. This. So the talk that I will present in some minutes is about how the security in a cyber-physical system. I will introduce what is a cyber-physical system. It's addressed using the control theory perspective. Security in let's say in cyber systems, it's been addressed from many other perspectives. For example, from the computer science perspective, from the communication perspective. So security is an important topic nowadays because, as you know, probably you have seen in the newspapers or in the news on TV, there are many attacks, cyber attacks affecting critical systems and infrastructures in most of the countries in the world. So this is an increasing concern for the authorities to develop and do research on new methods to guarantee the security of critical infrastructures in a country. In that context, this project Acroba, I was presenting you at the very beginning, that it's founded by the Spanish government through a program of cybersecurity of infrastructures. It's here presented. You can read more about other projects related to this topic in the framework of this research program. So coming back to the talk, my talk, let me present a bit the outline. So a bit the motivation I already did at the very beginning of my talk, but I will motivate a bit further. Why we need to develop new methods of security for cyber-physical systems. I will introduce this concept in more detail in some minutes. And why, from the control point of view, why not using the tools that people from computer science or communications use? What is the need of this new set of methods we are developing? Then I will introduce a bit the typical formalization of the attack detection and formulation that from the systems theory we consider in a very simple manner. Later on, Andreu and Pol will introduce in a much more elaborated manner. And also I will present some of the attack and adversary models that we can find in the literature, just to give a bit background, a flavor of the kind of models and attacks people is considering. Of course, it's not exhaustive. There are many more manners and many more attacks in the literature that people consider, but it just is to present a bit the kind of models and attacks that the majority of people is considering nowadays. And at the very end, I will introduce a bit some key references for the people that is more interested in this topic, can go in depth in most of the concepts and ideas I will introduce very briefly during my talk. So let me start with the motivation. So let's introduce what is a cyber-physical system. Probably you know about this concept. It's a concept that has gained a lot of attention in the research literature in the last years. because it's an important family of systems that has appeared when combining network computing systems with control systems. And this combination of networked computing and sensing resources with the physical systems introduce new problems, not only from the security point of view that I will introduce in this talk, but also from the control perspective. So in other talks, probably you have or you can understand better all the problems differently from the ones I'm commenting here, like the problem of control, distributed control. And there are many, many problems related to this interaction between networks, communication, sensing, and physical control systems. In any case, in this particular talk, the focus will be dedicated to the attacks and a very related problem that are the fault. But I will distinguish also on my talk what is a fault and what is an attack, because especially in the literature, there are a lot of confusion about these two types of concepts. In the literature of attacks, some people is considering the faults as a particular kind of attack, but as you will see, it's a little different. So unfortunately, when we have a cyber physical systems that has a lot of benefits because allows much more flexibility in the control and in adding a lot of additional performances like access to the cloud, access to the communications, access to very advanced AI technologies that we have nowadays, also introduce new problems. The problems is that some malicious agent can affect our system, introducing it in the communication system or in the control system, some attack. And this is the goal of my talk, to introduce how a malicious agent can affect the normal behavior of our cyber physical system. The difference from the attack perspective that people from computer science or communications and our perspective from the control theory point of view is that we'll deal with physical and cyber aspects, not only logical aspects that are addressed in computer science or in communications, the cyber aspects, but also the interaction of this cyber with the physical control systems. So this is the particularity of the approach we are presenting here. We are not only dealing with software protecting our system in a logical or software manner. We also are interested in detecting the attacks at the physical logical level. This is a bit very particular of the control systems, and this is why people from the control community has started researching on that topic. Problem of security in the cyber physical systems, as I said, thanks to the communication of these systems through the internet or the communication systems, make the control systems vulnerable, because usually in the development of the classical control systems, the security issue was not a concern because typically the systems are isolated, are not connected through public networks or internet, and the access to these controllers, it was very difficult from outside the plant. However, when these systems are interconnected, the remote access is possible. And even though this increase the functionalities, as I said, also create the problem of the attacks. In the past, this problem even was not considered. And in most of the industrial control systems we find nowadays, there are no protections. So you can enter in the system and you can do everything you want. This is what opened the door to the attacks, especially for systems that are not protected. Later, I will provide some examples. So the point that makes this issue also critical is that the physical systems in control systems need to include new functionalities of security, additionally to the functionalities that are classically used in every IT system in a company. In a control system, we have the possibility to affect the physical part. So we need to add in the control system new functionalities to detect the manipulation of some signals from the sensors or from the actuators or even the controller itself. So the necessity of adding security at this level is what motivates, as I said, the development of these new methods. So just to see some examples, there are many more. In the literature, there are already some reported attacks affecting plants and creating some damage. These are not faults. It's not because the plant has some fault and because the system presents some malfunctioning. But the malfunctioning was induced because some attacker entered in some of these examples in this uranium enrichment plant, or this steel mill in Germany, or this water treatment plant in Australia, or in the port grid in Ukraine, inducing a bad behavior of the system to damage in a volunteer manner the operation of the system to create damage. A fault, on the other hand, is something unexpected that appears because some component or some device in the system is not working as expected. So in one case, it's not volunteer. Fault attack is volunteer. Someone enters in the system and in a malicious manner create a bad behavior of the system. In fact, one of these, let's say, attacks that is called, that is known as one of the first important attacks, opened the doors on what is called the cyber war. Some countries realize, in the case, for example, of this uranium enrichment plan, that is a manner to do the war. Before that attack, it was not considered that was possible to attack another country using computer systems. So in this case, it was shown that it's not only affecting the data, like in a classical IT attack, where you enter in the IT system, you manipulate some data, or you access to non-permitted data to do a bad use. But here they realize that you can destroy physical systems, that they can access to the control systems of this plant, and they create a bad manipulation of some of the actuators to damage the plant. So this opens the door to do the work through computer systems, because you can do something physical. Before that was only logical. And this is what opened the door also in the research community to see that we need new tools to protect us against these cyber physical attacks. So this create, as I said, a set of new challenges that were not previously addressed in the control community, because before these, let's say, problems, there were a lot of literature dealing not with attacks but with faults. As I said, a fault is an attack, but a volunteer, we can imagine. Is that it's not an attack done in a malicious manner. It's something that occurs in an unexpected manner and then create damage in the plan, but not in a volunteer manner. Well, the attacker is a rational entity, so tries to enter in the system and create a damage in a volunteer manner. So this creates new scenarios, new problems that with the classical tools that were developed in the control community for detecting faults were not directly applicable when the fault induced in the system is done in a volunteer manner by an attack. Some examples that show this difficulty are called stealthy attacks. That is a type of attack that the attacker is introducing in the system to introduce a fault or damage in a manner that is not even detected. So this creates a lot of challenge in the systems we have to protect the plant or the installation, because with the normal fault detection systems, we cannot detect this kind of attacks, because the attacker is using some strategies to avoid that. Just looking at the classical indicators that in fault detection we use, the residuals, we can notice that the attacker is doing something malicious in the system. So, as I said, this creates a set of new challenges in the control community, trying to propose new problems, like the development of tools for assessing the risk, developing realistic adversary models. I will introduce later some examples. To develop new secure system architectures that are able to introduce some physical redundancy or even to detect where are the structural vulnerabilities to protect them against the attacks. Another particularity that makes the detection of the attacks in control system challenging is differently from the IT attack detection schemes that we have nowadays in most of the institutions, since we have to deal with signals coming from sensors or from controllers. We need to do real-time the detection. So that implies that our algorithms should be able to run in real time. So some of existing algorithms are quite interesting, but require a lot of computational time. So the algorithms that we develop in that context should be able to be run in real time. So every time that we get some information from the sensors, we need to process these informations to see if we can detect some malicious behavior in the loop. Another important challenge is that once we have the attack detected and we know what is happening in our control system, the next step is what to do. To stop the system, to activate some mitigation action, to reconfigure the control loop. So we need to think about some response to the attack to see if we can create some countermeasure to protect the system against this attack and avoid that the attack creates real damage. So after this motivation that shows why the field of security in control is being developed, let me introduce a bit the formalization that we use in control. As I said, probably if you look some other books or other presentations dealing with security, you will be a bit surprised with my introduction now, because we are trying to formalize the problem of attacks in the context of the control or the systems theory. So instead of formalizing the problem of attacks using software logic algorithms, here what we are doing is we are adapting the systems theory to deal with the attacks. In particular, this is an example. So let's consider the classical formulation of a system in discrete time. Usually the algorithms in attack detection in the same manner as in the fault detection are formulated in discrete time because the data that we receive from the sensors comes in a discrete time manner. So let's consider that we have a system in discrete time. Here it's in the simplest manner we can represent a system in a linear time invariant manner, but there are methods that use other representations, as you will see later. But the most developed methods assume the classical linear time invariant representation that is presented here, where we consider additionally to the noises and the disturbances that we typically have in the system, another term that could, in this case, affect the input, but we have also the possibility that can affect the output, that takes into account the anomalies, the behaviors that are not expected. These are anomalies in the context of the attack detection represents the attack. This is one possible manner of representing attacks. There are many more. As you will see later when I present the attack models. For every attack model, there are a particular manner of doing the modeling. So here is just a simple representation to say, when we consider the attacks in the systems or control theory, we are considering the classical representation of the system that we are using for control, but enlarging the model, including the attacks that, of course, are unknown. And our task as developers of algorithms of attack detection is to develop algorithms that are able to detect those attacks. But this has a challenge, is that our systems, as you know, also are affected by some other, let's say, signals that make this detection challenging. Because as you know, and as I said, we have disturbances, we have noises. So we should be able to distinguish if we are detecting is not the noise or the disturbance, but an attack. So when we develop our algorithms, always there is a trade-off between the performance of the attack detection and the existence of these uncertainties that affect typically the system, that are the noises and disturbances. In the literature, the characterization of the uncertainty, it's been developed in many manners. So some methods consider that the sources of uncertainty can be represented in a statistical manner, typically Gaussian manner. So one manner to characterize the noises, disturbances, is to assume that they follow a Gaussian distribution, as for example in the Kalman filters or similar approaches. There is another field of control that, instead of assuming that the uncertainty is represented in a statistical manner, Gaussian, assumes that the disturbances are bounded. It's called the deterministic approach. So in this case, the noises and disturbances that we should consider, the only assumption that we consider is that they are unknown but bounded. So here the challenge is to develop attack detection algorithms that are able to perceive these anomalies, these attacks, and distinguish them from the uncertainty. So in some sense, this problem is called the robust detection problem, because we need to be able to establish this trade-off between attack detection and uncertainty rejection. So the typical problem can also be formulated as follows. We will have from the system some data that typically, as you will see later, comes from the communication networks. As I said at the beginning, we are assuming that our plan and our controller are connected through a communication network. This is why it's a cyber-physical system, because we combine the two elements. So the connection is typically done through the network. And we typically distinguish what we have from the plan side, that is the input and output that the plan receives, from what we have from the controller side. That is what the controller sees. So, and between the two, we have the network, that is where the attacker can inject or can manipulate the information to inject the attacks. So when there is no attack, this signal, this F, that this is the signal that I was commenting represents the attack, is zero. So there is nothing, just the random behavior of noise and disturbances affecting the system. And in this case, the input of the plan and the output of the controller are the same. And the same happened with the output of the controller and the input of the output of the plan and the input of the controller. So the signals that controller and plan send and receive are exactly the same. As you will see later, when we have attacks, this is not anymore true. The attacker can manipulate this connection between the plan and the controller, and this equality that exists is not anymore true. And because of the attacks, there is some manipulation in the communication between the plan and the controller. Additionally, remember that we have a control system. So additionally to the plan is controlled by some controller. Here, I just introduce the simplest controller, that is an output feedback control that is represented by this structure. Of course, here, as you know from the control theory, there are many more controller schemes that we can consider. I just select this because it's quite a standard, and in most of the techniques is the one that is assumed. So additionally to this, additionally to have the plan, to have the controller and the communication channel that interconnects the plan and the controller, the task of the algorithms that we develop is to develop some anomaly detector. In our case, the anomaly is the attack. Some algorithm that reading the informations that interchange the plan and the controller, and using some model, also some methods use just data and are called data-driven in this case, analyzes the information from inputs and outputs controller and plan, and using, for example, an observer, generate what is called residual that in a normal situation should be close to zero or just bounded within the thresholds that are determined by the uncertainties associated to noises and disturbances. But in the case that some anomaly appears, some attack occurs, this residual is not anymore bounded by the effect only of the uncertainties and the disturbances. And then we detect some incoherence in our algorithm that allows us to trigger some alarm. And here is where the attack detection starts. Of course, this is just tell us that we have an attack, but still we probably don't know which kind of attack we have. As you can see later in the presentation, there are many types of attacks. So another important task is to know which is the type of attack, because probably depending on the type of attack we have, the reaction that we have to do, the countermeasure that we need to activate could be one or another one. Anyway, this is part of my talk in the next slides. So what is important is that we should be able to generate some signal that is sensitive to these attacks. And when we detect that this signal is indicating an anomaly, is when we assume that there is an attack. Of course, because of the existence of the noise and the disturbances, maybe there are some false detections that we need to avoid. And this is why our algorithms should guarantee that are robust against all these existing uncertainties we have in the data. So this is the full scheme we have, just in a graphical manner. We have the plan on one side. On the other side, we have the controller, and we have the detector. That there are many configurations, of course. This is one possible configuration that analyzes the information that is received from the plan and the controller is sending to the plan, and using, for example, an observer or some other schemes that exist, detect some not normal behavior. You detect an abnormal behavior, and in the case of the context of attacks, it's categorized as an attack. Here, as I said, there are quite a lot of similarities with the fall detection, but there are, as I said at the beginning, even though some ideas can be reused from the fall detection, in the attacks, it's much more challenging because, as I said at the beginning, the attacker can do some action so that the attack cannot be directly perceived. So we need to inject some additional information in the system, as for example, some additional signals you will see later, that allow us to facilitate the detection. Because maybe just with the readings we receive from we are not able to see anything, as I said. This creates an extra challenge that in the fall detection we don't have. So after introducing the formalization of the problem in the context of the control theory, introducing the different ingredients, now let's talk a bit what are called the adversary models. So to detect the false, we need not only to model the system, model the controller, think about a fall detection, an attack detection scheme, but also typically, depending on the type of attack, the algorithm should be adapted to the particular type of attack. So to characterize the different type of attacks that an attacker can do, in the literature, it has been categorized the type of attack depending on the resources the attacker can gain. For example, some attacks or some attackers assume that they have some a priori knowledge about our system. For example, they know the structure of our system, even they know something about the model of our system. So one category of information that the attacker can use is the knowledge of our system. And also depends on the type of accesses that the attacker will do in our system. If access to information that is very sensitive, sensitive information. This is known as the disclosure of the resources. The attacker has access, for example, to the information interchange between the plan and the controller, and gains information about this interchange, and can manipulate maybe this information. Or maybe the attacker can create a disruption, can cut or manipulate the information that the controller and the plan are interchanging. And this is called a disruption of the resources. So depending on the information and the sophistication of the attack, as you will see later in the classification that I will introduce in some slides, the attacker can do a more or less elaborated attack. Also, additionally to the resources that the attacker knows about or can gain access regarding our system, there is the attack policy. Is the strategy that the attacker, considering the information the attacker has regarding our system, generates this attack affecting our system. So putting all together, in the literature, it has been created what are called attack models. And in this graph, what we have is the three axes of information I was presenting before. So the knowledge of the attacker regarding our system is the vertical axis. This is the knowledge regarding the model or the structure of our system. And if the attack is accessing the information the controller and the plan interchange, this is the disclosure access, or if the attacker is manipulating the information or disrupting the information interchange between the controller and the plan. This is the disruption axis. So based on these three axes, the different attacks that are more or less studied in the literature are here presented. I will explain later about these attacks. But for example, there are some attacks that use everything. It's the covert attacks. They have knowledge about the model, disruption of the resources, or disclosures. There are some others that only disrupt the connection, like the denial of service attacks. So depending on the type of attacks, use more or less information about our space to generate the attack. So this is a classical classification that you can find in the literature, and that it's used later to model in a more precise manner these attacks and things about countermeasures, because when and also develop the corresponding attack detection mechanisms. So basically, we can summarize then that the attacker has a goal, has a purpose. That is, as I said at the very beginning, is impact the system operation, typically to create damage or just to destroy our system or make it not operative anymore. So the idea is that at a given time instant, we want to guarantee that our system is operating in a safe manner. We want to guarantee that our system is operating in a region of operation that is not affected by attacks, while the attacker is trying to do exactly the contrary. He's trying to move our system from the safe operation to a non-safe operation. So moving the behavior of the system out of the normal set of operation for the system. On the other hand, additionally to this goal that it impact the system operation, there are some constraints on the attack. The attacker, as I said, typically wants to achieve this goal trying to remain undetected. That is called, for example, a stealthy attack. What is happening in the stealthy attack? So this is different from the fault detection. A fault, since it's not done by purpose, typically doesn't have this characteristic. The fault typically appears because some component is not operating as expected because of some unexpected situation. But the attacker, additionally to create this problem, to create a fault, is trying to do it in a manner that remains undetected. And this is very challenging compared to a fault, because the fault doesn't have this characteristic, as I said at the very beginning. So the idea is that the attacker is trying to introduce the attack in a manner that in the period the attack is active, the residual, that is this indicator that we use to detect typically the attacks, is undetected. And this creates a lot of challenge in the development of the attack detection. That is not the case in the fault detection. So after introducing a bit the different ingredients to characterize an attack, also to introduce the ingredients of the attack policies, the models of attacks, and also the elements of cyber physical systems, let me introduce a bit some examples of attacks that affect the cyber physical systems to try to see what is really an attack. Because I was talking for quite a long about attacks, but I never said exactly which kind of attacks are considered. One of the most classical ones, not only affecting cyber physical systems, also affecting servers in the web. Probably you have heard in the news that some website is down because this denial of service attack has occurred. The denial of service attack is a very classical attack that is not only used in the cyber physical systems, it's also used in normal IT services. That basically occurs because the attacker enters in the network of the system, in this case, in the network of the control system, and injects a lot of information, a lot of messages, typically. So creates what is called a flooding of information that collapse the communication system and prevents that the actuator or the sensor reach the destination. So depending on if it is from the controller to the actuator or the sensor to the controller. So the denial of service disrupt, as I presented before in the diagram of the different ingredients of attack, disrupt the communication between the controller and the plan. In this case, fortunately, can be detected, but create a lot of trouble because you lose the control of the plan. So after a denial of service, probably the controller is not able to guarantee the operation of the system in a safe manner. So because the loop is open, or not completely open, but disturbed in a manner that the control of the plan is not anymore possible or is degraded in a manner that can be dangerous. So the idea then, as I said, is that once the attacker gain access to the communication network, the attacker can, as I said, jam the communication channels, compromise the devices that communicates, controller, sensors, and prevent them from sending data. This can be done by attacking the routing protocols and flooding the network traffic, difficulting this communication. In the model of attacks that I was presenting before, if we try to characterize this attack using the 3 axes I was commenting before, this attack is quite simple, can be done without any knowledge of the system, so it doesn't require any a priori information about the system. Also, there is no need of knowledge about the information interchange, and the only access that it's considering is the disruption, as I said before, because the data channels are made unavailable. There are 2 strategies for implementing this denial of service. One is called the zero input strategy, that in this case, basically the connection that is completely disrupted. If you remember, as I said before, without no attack, the inputs and outputs of controller and plan are equal. But when this zero input strategy occurs, either the input or the output is completely forced to be 0. And this is called the zero input strategy. Or another way is of doing this attack is through the hold input strategy. That in this case, the values are blocked to the last value receive or send. So depending on the attack, could be of one type or the other. So the information loss that is denial of service attack introduced in our system, in the literature, it's mathematically modeled in some ways. So to characterize this attack, in the research literature, there are many manners of modeling this, like, for example, using Bernoulli models to characterize the measurement control packets that are randomly lost. So adding some probability of loss, some Markov models, some time delays, some periodical PWM signals. So there are many manners of modeling the attack in a rigorous way through mathematical models. And once this denial of service attack is modeled, then the algorithms use this modeling to develop the strategies of detection and mitigation. Another very famous attack that is in the literature, and in fact, it's inspired in what the other type of, not attacks, when there is a robbery in a bank do, is the replay attack. The idea of the replay attack is a kind of attack that is based on, there is a phase where the attacker records the normal operation of the system, in particular, saving the values of the sensors and actuators in the normal operation. And once this is done, then the attacker reproduces this data to the controller or the control system and is able to manipulate the recorded systems in a malicious way. It's like, as I said, when a robber goes for a robbery in a bank, is gaining access to the cameras that monitor the bank, and then reproduce the normal situation where there is no robbery in the bank, and the people that is monitoring the cameras, they didn't realize that someone is robbing the bank. So it's the same as spirit. In fact, this was the strategy that was done in this Stuxnet case, that is this attack to this nuclear plant in Iran. So in this case, if we take into account the attack space that I was presenting before, in the case of the replay attack, there is no, again, a priori knowledge about the type of system we have. It can be done without knowing the structure of our system. And the modern knowledge that is only interesting to make more, have more interpretation of the information that we access. There is also, and on the other hand, the disclosure of resource, because the attacker is able to access the data channels and creating what is called the eavesdropping of the information by means of the attack. And regarding the disruption of the resources, the data channels that the attacker affect, plus the injection maybe of some malicious information to replace the right information that the channel has. So as I said, this attack has two phases. One phase, the attacker records the normal operation of the system, and this is used later to reproduce to the control system or the people that is monitoring the system with the normal operation. While in the second phase, the attacker manipulates the information and gains access to our control system, forcing some bad behavior, creating some robbery of resources. For example, some people in Mexico use this to access to the pipelines that transport fuel to rob the fuel, and sending to the control system or monitoring system, supervision system, the normal flows. Another important attack that is studied in the literature is called the false data injection attack. In this case, the goal of the attacker is to inject some malicious measurements or inputs to disrupt the system operation while the attacker remains undetected. Of course, in this case, it's more challenging because to implement this attack and being undetected, no, typically the attacker needs to know about knowledge of our system, because he has to do in a manner that is undetected. This can be done by manipulating the state estimation process, modifying the measurements that the state estimation is using, or injecting some bias, no, in the control actions, and in a manner, no, that is undetected. There are many more type of attacks, as I said, and this is just to give a flavor of the kind of attacks we are trying to deal with in the security of cyber physical systems using techniques from control. The topic of attacks is quite new. If you go to the literature, I mean, the first references that we can find are from the 2008, late, I mean, close to the 2010, is more or less when everything started. There are some seminal papers, no? For example, this first paper, where the concept of secure control was introduced in the context of the cyber physical systems. Later on, this, let's say, topic, it's been developed, especially after this Stuxnet attack. For example, here in the last reference, you have a description of this important attack that was like the beginning of the cyber war. It's called in that manner in the literature. No, how this attack was really done. It was studied in this paper, no, that presents the Stuxnet. There are other, let's say, references here, some of them that present the classification of the attacks that I was presenting you is the second references, and the formalization of the attacks in the context of control, and a bibliography review that we did in the past. Now, probably there are more recent ones. Also, just to show the importance of this, as you know, in the automatic control field, there is an important association that is called IFAC, the International Federation of Control, that has some technical committees at the international level. And there is one committee that is called Safe Process that deals with safety. And now, because of the concern of attacks, has been expanded the concept of safety, not only to consider false, that was like the main target of this community for a long time, to consider as well attacks. So now, not only false, but attacks is the goal of this community. And in particular, just recently, has created a working group of researchers to see how the theory that was developed in the past for safety in the sense of false can be extended to the security of the cyber physical systems. So now there is a lot of effort in this community as well to expand the knowledge that was before developed only considering false to deal also with the attacks. So if you are interested, I can provide more information about the activities that this working group is developing. So from my side, that's all. I don't know if the audience has some question, something that is interested to know regarding this interesting topic of attacks. Okay. If not, then as I announced at the beginning of this session, we'll move to the second presentation that is done by Andreu Cecilia, and he will present some of the research activities that we are developing in the context of this Acroba project I was commenting, that is the promoter of these seminars. So I allow Andreu to gain access now to the Meet and present the presentation he has prepared.
Okay, so after this overview presentation of cybersecurity in the context of automatic control, done very nicely by Vicenç, I will start presenting some of the novelties or the contributions that we have obtained in this research project, Acroba, founded by INCIBE. And in particular, in this talk, I will present how to detect two of the more complicated attacks to detect in cyber physical systems, that are replay and covert attack. So, as Vicenç already started explaining, the context of the type of detection mechanism or type of security that we want to develop here is that we want to protect systems that combines a communication network with an information network, that is the cyber part, with a physical part. And this physical part have some dynamics that we want to control, and we want to make it operate in an optimal manner. And what we have is a communication where we have some physical plant, we have some actuators acting on the physical plant, we have some sensors that provide information to a control center to decide what the actuator should do. And this closed loop is done through a open communication network. And just as an example of what this is physical, here there is a figure of an industry in China, that there is here all the buildings and different places where there is these actuators and physical plants, and the control center is located here. So we can see that there is like this geographical distribution in between the place where control signals are decided and the place where they are introduced. And the issue is that since you have this communication done through open communication channels like this, now there is the possibility of someone trying to intercept or interact with this communication network. And as Vicenç showed with different examples, this can be really, really, really dangerous. So once someone tries to design this type of networks and tries to develop control algorithms for these physical systems, it is very, very important not only to look for performance and optimality, but also taking into account these security issues that can appear. In the sense of how to do cybersecurity from a control perspective, again, this is like a different perspective from other people, maybe from computer science or communications. So what we are trying to do here is not preventing the cyber attack. So in the sense that to not prevent people accessing the communication network, or to not prevent people trying to manipulate this. This comes from more a computer science point of view. From a control theory point of view, we assume that this has already happened, and what we are trying to do is to detect, isolate, and mitigate this attack. Okay, so our point of view is complementary from the communication or computer science point of view, and is adding additional layers of security. So even if someone can overcome all the informatic security measures already in the communication networks, our layer adds more security to that, so we can detect it and we can mitigate the impact. And we want to do it in a automatic control perspective, in order to add mechanisms that can have minimal impact in the stability, optimality, and performance of these critical systems. And doing it from the automatic control perspective, it's very, very good, because this perspective gives us a strong theory on what means to be stable, what means to be optimal, and what means to have performance. So what we can actually do is to develop these cybersecurity mechanisms, ensuring demonstrable security and performance. In this talk, I will consider a very, very critical scenario. So if we consider a similar scheme as Vicenç presented, we have a plant layer and we have a control center layer that is deciding the control actions, and they are connected through an open network like this. The scenario that I'm considering in this talk is that an attacker has access to both networks, the control network line and the sensor network line, and can tamper both simultaneously. And why is this critical? because if the attacker is able to do this, now the attacker can do some type of cooperation between what is manipulating in the network of the control and what is manipulating in the network of the sensors. And if he can do this type of cooperation, actually very advanced control attacks from a control perspective can be injected on the system. And what do we mean by advanced attacks? Well, the thing is that most physical plants, industries, electrical grids, and things like this already have security mechanisms inside there. For instance, in electrical grids, there is already sensors that measure that if the voltage goes above some certain values, some security mechanisms are activated. And in chemical industry, there is same things with pressures, temperatures. So all these physical mechanisms already exist and are implemented. The problem is that if an attacker can do this type of cooperation, actually what he can do is inject malicious signals in the actuator, so the voltage of the grid can increase, the temperatures of chemical processes or pressures can increase, which this is really, really dangerous. But in cooperation, it can remove this effect from the data sent in the sensor received in the control center. So by doing this, in the plan layer, these variables are increasing dangerously, but in the control center, we are not detecting this, so these security mechanisms are not activated. This is why if someone can do this type of cooperation, it can be really, really dangerous. And in this talk, we are going to present two strategies that Vicenç already commented about the first one, and I will present about the second one, that are replay attacks and covert attack. What are these characteristics and what we have proposed in order to detect this type of attacks. So let's begin by replay attacks. So the idea, again, is that we have an attacker which can, in cooperation, manipulate the input signal and manipulate the output signal. So what is basically a replay attack is an attack where the attacker records from the sensor channel, records some values in a window, and then in the next window, he replays the values. Okay, so in here in the sensor, he will replay during the time t and 2t what has recorded between 0 and t. And obviously, since this is just a replay of what has happened before, if the attacker injects some harmful data in the actuators, the variables here can dangerously increase and will not be detected because this has no information of what is happening between t and 2t. So this is a very simple attack to do because you don't need to know anything about the plan that you're attacking or the security measures or nothing like this, because you just record and replay. And actually this can surpass a lot of common detectors. Why? Because if you have detectors based on thresholds, if some variables increase some values or not, obviously this cannot detect it because you will not detect if these variables are increasing or not. But if you have detectors based on maybe comparing the statistically what the signals are doing with respect to what should nominally do, you can also not detect it because this replay signal statistically is exactly the same as in the nominal case without any attack. So here we have something that through cooperation, very, very easy, it can surpass almost all detectors in the industry and actually can have very, very large impact on the plan. So what is the proposal of how can actually we can avoid this type of attack, or how can we detect this type of attack happening? Well, the thing is that the simplicity of this attack, that is that the attacker does not know anything about the plan, is just replaying data. This simplicity is what we as defenders can exploit to put a detection mechanism. So basically what we are going to do is to add in the control layer a watermark signal, a watermark generation that we are going to add in the control layer that is introduced in the plant. Okay, and this we are going to design it ourselves. And why this can overcome replay attacks, at least allow to detect them, because what we are going to do is to add a watermark signal. This signal will change how the plant is behaving, and in the observer, we can make a prediction on how the plan should change according to this watermark. If there is no attack, so if there is no replay attack, what we predicted that should happen and what is happening should be very, very similar. But if there is a replay attack and there is data being repeated before adding this watermark signal, there will be a discrepancy because we are expecting the plant to change according to this watermark, and we are not seeing this change in the signal. This is why adding this watermark signal allows us to detect. So just intuitively to understand, since replay attack is just replay recorded data, if we change something in the plan and we should expect some change and we are not detecting it, then we can deduce that someone is replaying our data and we can detect the attack. But the problem of this strategy is that obviously since you are adding additional things to your input, this watermark signal, you're affecting how the plant is behavior. So you are shifting the operating point of this plant, you are changing the optimality of operation of this plant, and there is things like this. So what we have contributed in this work is that even if we have non-linear systems, which are very complex to analyze, even if we have non-linear systems, we have actually developed an algorithm that allows us to co-design the watermark signal intensity through this matrix G, the controller applied in the actuators of the systems, and the observer used to detect attacks. We can co-design everything in order to maximize the detectability, in sense of we can increase the type of replay attacks that we can detect while keeping the effect of on the performance of the system bounded. So basically we have developed some indicators for nonlinear systems that allows us to define what do we mean by detectability and define what do we mean by performance degradation. And these definitions, actually, we embedded inside a convex algorithms in order to co-design and maximize detectability and keep performance degradation bounded. And just as an example of what can happen here, there is the results when we apply this technique to a robotic arm. So a robotic arm obviously is a very non-linear system. So usually standard techniques from cybersecurity community that focus more on linear systems will not work here. So we have a robotic arm and we are adding this type of replay attack on the system. So the replay attack starts at 70 seconds. And what this replay attack is doing is replaying data, and then we are injecting some malicious data. So here in the clear blue line, we can see that if there is no watermark or no mechanism, the signal, this signal G, that is some signal that we use to detect, is kept at 0. So actually we cannot detect anything. So someone is tampering with this robotic arm and we are not detecting anything. Then by adding a watermark signal, actually we can see that when the replay attack happens, now this G starts moving. So we can see how this discrepancy between what we are expecting from the observer and what is actually happening can be exploited to generate a signal that actually grows. And the next thing is that using our algorithm, actually we can increase the detectability of exactly the same attack. And we can see how after improving, that this is what is happening in the red, that is improving the parameters of the controller, observer, and the watermarking, we can increase the detection of this type of attack. And why it is useful to maximize detectability, because usually you put a threshold in order to know that if this signal is above this threshold, you are having a watermark attack, and if it's below, you are not having this watermark. So without improving, we can see that this threshold, some points, it is not overcome. But in the red, we can guarantee that we are always going above this threshold. And here, we can see how the performance degrades when we are using the protocol with the blue lines or the optimized ones. So we can see some differences, but actually using our indicator, we can guarantee that the performance is bounded, so the effect is not very large. So now I will move to the second type, that is the covert attack. So again, this type of attack requires a cooperation between manipulating the actuator signal sent it to in the actuator and the sensor received the signal received from the sensor network. But this type of attack is more advanced than the replay attack, and actually is much harder to detect. So what is this attack based? Is based that what you are basically doing is injecting some signal in the actuator path, and then in the sensor path, you add a signal that will remove completely the effect of the attack. But you're removing the effect of the attack just on the data transmitted. In that case, here in the control center, we will not detect anything because the effect of the attack has been removed from the data, but the plant will be affected by the signal. So this is a completely stealthy attack. Now, how can you actually design this? How can you remove from this side the effect of the input? Well, if this plant was completely linear, actually it's very simple to do, because the only thing that you need to do is to add what is being computed here in the sensor path. So what this equation means is that if UA is the signal that you're injecting in the actuators in order to manipulate these variables and make it dangerous, A, B, and C are matrices from the plant of this system that describes the dynamic of the plant. If you compute YA with these dynamics, which is just using UA and doing this, and you add this term in the sensor data path, the effect will be completely removed. And why is this the case? Well, it just comes from linearity properties of linear systems, that basically the effect of the nominal actuator plus the attack signal, the effect on the output will just be the addition of what will happen with the nominal controller plus what should happen if I just do the attack signal on the plant. And here we are removing exactly what is happening with the attack signal on the path. So this is a more advanced attack strategy, because you actually need to know the plant. You actually need to know the model of the plant in order to know how to exactly remove the system, but is extremely dangerous. So what we have proposed here is something that is a little bit better than just adding watermark signals or doing moving target defense. Is that what we are going to exploit is that, since in order to do this type of covert attack, you need linearity of the plant. So this plant has to behave linear. If it does not behave linear, this will not work, because you cannot separate additively the effects of the nominal controller and the attack controller. What we are going to propose is to add an auxiliary non-linearity in order to break this linearity on the system. So just to show you that if we are not changing anything, what is happening when you apply a covert attack, here we implemented this type of strategy, this type of covert attack in a electrical grid, in the converter of electrical grid that we have in the laboratory of Universitat Politècnica Catalunya. And basically what we do, as we have here, is that we have some reference voltage attack that we are manipulating. So at the very beginning, the first 60 seconds, the reference voltage that we are sending to the converter to follow is just the nominal, and there is no attack. And after these 60 seconds, what we are going to say is that the reference voltage sent to the converter through this network, we are going to increase it and put it in this 1510, 1510. So what happens then is that the converter will increase 15 volts or 10 volts its voltage, which this is extremely dangerous. However, by doing our technique, actually we can create another signal, that is this YA, that we can add in the sensors. These are the different signals that we can add in the sensors. So the voltage actually measured and received in the control center will not see that we are increasing or reducing these 50 and 20 volts. Then actually this we can see what is happening in the signal. So we can see that after some times, the voltage has converted to 60, which is the nominal value that we required. But after this 60, even implementing the malicious signal injections, since we are removing the attack, we are still measuring the nominal voltage of 60. But what is truly happening in the plan is that the voltage is increasing from 60 to 75 to 70 and things like this, which is really, really dangerous. So how can we avoid this? So as I said, what we're proposing is that in order to avoid this type of very, very dangerous attack that are covert attacks is to break linearity of the system. So what we are going to do is that just in the plant layer, we don't even need to do anything in the control layer. We are going to add an auxiliary non-linearity. So this non-linearity is designed in order to break this linearity of the system, and then the covert attack cannot be done. The properties of the approach that we are proposing is that, okay, we are adding non-linearities, and at least from a control perspective, or the dynamical system perspective, adding non-linearities is always scary, but we have designed an auxiliary non-linearity that preserves the stability of everything and performance by construction. Also, doing a very similar convex algorithm program, we can actually optimize the nonlinear function in order to maximize the detectability of covert attacks. And the thing is that once you have designed this nonlinearity, the application is very, very simple. Why? Because you only need to add this nonlinearity in the plant layer. You don't need to add any additional communication channels. You don't need to add some type of synchronization between endpoints. You don't need to change the model or the plant or anything in that way. So this is very, very simple, and it's much simpler than other strategies that you can find in the literature. And here, again, repeating the same experiment as before, but adding our protection layer. Here we can see what happens with, again, signal G that is generated by the detector in order to detect attacks. So again, we are going to inject to our electrical grid the covert attack at time 70 seconds. And here in the red is what is this detector signal doing when we apply our auxiliary nonlinearity. And here in the purple line is what is happening when we are not adding the auxiliary nonlinearity. The blue and green are just some thresholds in order to detect the attack. So we can see that without the detection mechanism, the attack is completely undetectable and they are manipulating the signal. However, when adding this auxiliary nonlinearity, this detector increases significantly and we can 100% be sure that the attack is happening. So I would like to finish by saying that, again, all these developments have been done in the context of the Project Acrobat, founded by the Institut Nacional de Ciberseguridad. Thank you very much for your attention. I don't know if you have some questions regarding this work. Okay.
I have maybe one. So this
Yes.
implies that the plant always has to have linear dynamics, no? For this to be.
Yes, so to apply the covert attack, you can only do it for linear dynamics plans.
Okay.
Yes.
And are there issues concerning maybe the delays on the sensors or the communication layer that may affect the efficiency, let's say, of your approach?
Well, the thing is that what we are basically doing, instead of moving the detector, what we are doing is just adding additional things on the system that breaks the possibility of doing the attacks from the very beginning. Then if there is delays in the middle, or you have this, I don't know, the communication is in discrete time, there is delay, there is package losses, the only thing that you need to do is to take into account them in the detector in order to optimize how you detect these type of things. But this is like a second iteration of what we are proposing. So what we are proposing by adding the watermark or by adding the auxiliary nonlinearity is to add some additional things on the system that do not modify a lot the performance, even if there is these communication delays and things in the middle, they do not modify the performance, but they break the possibility of having completely stealthy replay attacks or completely stealthy cover attacks.
And can both methods be applied simultaneously?
Yes. Yes. Because obviously, if you have the auxiliary nonlinearity and someone does the replay attack, you will not detect it, but you can add the watermark signal. Actually, one of the things that we work a lot is that the type of stability properties and the type of performance indices that we develop for all the techniques, and also the ones that Paul will present later, we are using the same indices and the same performance indicators, in the sense that if you want to combine all the ideas simultaneously, you can actually do it, and you can actually optimize the detection of all the things simultaneously.
Maybe I was lost somewhere, but is there a preferred or typical type of nonlinearity that is the additive you choose?
Yeah, so usually in this type of nonlinearity, what we like a lot, that is what behaves very, very good, is that you want some nonlinearity that if you are close to your operating point is 0, if you are close to the region of the attraction of the operating point or the region that you want to operate is very, very small, but once you are far away, that is what usually the attacker wants to do, it grows very, very far, very, very fast. So basically, what we design is, and this is what in practice works really well, is some type of Gaussian function that is 0. Well, the inverse Gaussian, let's say, so it's like a concave valley that is 0, but at the very beginning it grows slow, and then after that it grows really, really fast. So this nonlinearity works really well because it does not affect a lot the performance of the system. But if someone wants to actually tamper in a significant way the system, you will detect it very quick.
This type of nonlinear signal can be, is there like an analytic method to design it? Like
Yes.
just follow these steps?
Well, I have not presented here because it's more technical, but all these properties on how fast it grows and in which regions it grows and all these things, all these properties we can represent it in something that we call quadratic abstraction, that is just quadratic constraints on the nonlinearity. And these quadratic constraints can be embedded in a linear matrix inequality with everything being constant. So actually you can solve some type of convex problem through linear matrix inequalities to find these matrices, define the quadratic abstraction, and then define the function from that. So yes, so we have developed something that is very methodological to design this function.
Nice. And also you said now that the, let's say, parameters of the nonlinearity, they are constant. Is there a scenario in which maybe a variable nonlinearity would be beneficial?
Yes.
Maybe some different type of attack?
Yes, actually, this is in here. We implemented auxiliary signal that is non-constant, because basically by structure, this auxiliary nonlinearity preserves the stability of everything. And actually what you can do is that you can change the function phi in the matrices G and H without changing the stability of performance of the system. So actually you can do a protocol that at random times or at random things, this function here is modified. And this is actually what we implemented here, and we can actually still detect the attack without affecting the performance of the system at the very beginning. Here at the very beginning, we are doing this switching of function, and the detector is still the same because the plan behaves exactly the same, but after we can detect it. And this is really, really powerful because you can just imagine any type of protocol of switching the function. This is very helpful because if someone knows that you are doing this strategy and try to identify the function somehow doing system identification. So he tries to measure U and Y. Since he knows the plan, he tries to identify the nonlinearity. Someone tries to do this. This switching protocol will completely prevent it. And since the nonlinearity is only applied in the planned layer and not in the control layer, you can do very crazy switching protocols, and you don't need to add any type of synchronization between both sides. So it is very, very secure.
But this then implies that for the methodological approach that you have for designing the nonlinear function, there are multiple possibilities of
Yes.
for the same applying the same method. You arrive to a result where you have a bank of
Yes.
possible functions.
Yes. Correct.
Okay.
Correct, because we found a family of functions that guarantees you some performance and detectability, and then you can choose from this family, and you could switch between this family in this switching protocol.
And just a stupid question, but I saw that all the errors I think you showed are additive, like in summing, but for subtraction they should also work. No, it's not an issue.
Yes, obviously.
Okay.
Yes.
No more questions. Thanks.
Okay, so if there is no more questions, I will stop sharing, and then Paul can do the last talk of the day.
Ok. A ver. Vale, perfecto. Uy. Ok. Okay. So thank everyone for coming. My name is Paul, and I'm here to present, well, a review of my latest work, which we'll call here control theory-based methods against eavesdropping and FDIAs in distributed control systems. This year in this presentation, as I said, I'll give an explanation on one of my latest works in the framework of my doctoral program and also in the frame of the Acrobat project, in which I'm studying the problem of secure control and estimation algorithms in smart power grids. As is well known, a smart grid is a large-scale cyber-physical system whose goal is to provide electricity from local to countrywide level. And this work addresses a theoretical part of the final objective, which is to implement secure control algorithms in small-scale smart grids. Okay, so now the layout of this presentation will be the following. We'll have first a brief introduction, which I'll shorten a bit because both Andreu and Vicenç gave a brief introduction on cyber-physical systems and cyber attacks. Then I'll go more in depth in how we classified cyber attacks in my framework and how did we choose the method and the type of attacks that we try to defend and in this work. Then, before passing to the results section, I will give a brief introduction on multi-agent systems, which, as you will see, are a kind of dynamical system which are used to modulate large-scale systems which operate individually just with its own information and the neighbor information, as you will see. And then finally, I'll pass to the results sections where I'll explain the work done. Okay, so, sorry. First, let me introduce, well, as also Vicenç have introduced before, a cyber-physical system is a large-scale system whose dynamics, or the dynamics that affect the system or matter, are not only on the physical layer, but also are influenced by cybernetical aspects. So some common examples are smart grids, as the ones with I work in my thesis, autonomous vehicles, in the industrial field, medical, military, aeronautics, etc. So cyber-physical systems, as mostly are implemented through open communication networks, they are open to the threat of cyber attacks. And that is where the secure controller estimation branch from control theory appeared, as by definition is the problem of designing the control estimation schemes that, apart from trying to achieve the classical aspects of classical control, such as performance and stability and robustness, we also try to keep the data safe, valuable, and confidential. So now let me give a brief review and recap the the typical cyber attacks that have been studied in literature. So cyber attacks, as Vicenç explained earlier, can be classified in 2 dimensions, which are the attack space, which tries to tell us or characterize the attack depending on the resources that are needed to carry them on, and the impact space that tells us where in which areas does the attack affect the plant. And it may be the system dynamics, the actuators, that is the devices that apply the control signals to the plants or the targets, and the sensor, which are the ones who read the signals who are sent to the network. Okay. Starting from the classification that Vicenç said earlier, here in our context, we classify cyber attacks in 3 main families, which are eavesdropping attacks, which only try to steal the data without being noticed. Then the false data injection attacks, which try to modify the data that is being sent through the network. And availability attacks, which are basically denial of service or jamming attacks, which just try to make unavailable the communication network. In the framework of this work, we are focused on eavesdropping and false data injection attacks. So, as I said, an eavesdropping attack is an attack where an unauthorized interception of the data is transmitted between 2 communication endpoints. That is, an eavesdropping attack, as I said, tries to steal the data, and many anti-eavesdropping methods, what try to do in order to avoid that, or to prevent the eavesdropping attack to be successful, is to destroy the observability of the data. And that is that the data that is being stealed, cannot be used for other for things like trying to, for example, estimate the internal dynamics of the system or get more information of the target system. By the other part, false data injection attacks try to modify the system dynamics to the attacker's desired behavior. In order for an attacker to perform a successful false data injection attack, its goal is that the measurements that try to be modified, that is the attack signal, as Andreu told before, is that such signal cannot be detected by the anomaly detectors. And that is done in a more mathematical, try to explain it in a more mathematical way, is that the attack signal is not in the column space of H, where H is the measurement function of the state of the internal state of the plant or the target. So both eavesdropping attacks and false data injection attacks usually come down as they go together. So most of the methods that exist in literature try to avoid both types of attacks at the same time. So the most relevant methods that have appeared in literature and are most relevant are the following. The first one is different private noise injection, in which, similar to the work that Andreu explained before, random noise is injected into the network in the control loop, so that the data that the attacker tries to access is not useful in order to perform like a system estimation. So the problem with differential privacy is that as the source of noise is completely random, such noise cannot be removed from the source. So that you must perform a trade-off between privacy and performance. Then there's also homomorphic encryption, which tries to carry out classical cryptography on the line, such that what you have to do is just encode and decode at the end of those lines. This is the most classical and direct method, and is the more strongly secure. But its problem is that such cryptographic search in the computation of the data can carry some critical delays in the control loop that might bring to some critical situations when you are working with real-time scenarios. Then the next would be moving target defense, where the goal is to modify the output function continuously. I mean the output function of the targets, so that the attacker cannot identify correctly the plan. And finally, the method that we also have been working are encryption via masking signals. that is the same work of or similar work to what Andreu did in his work. And it's basically the injection of a noise signal, but differently from differential privacy. In this case, such signal can be removed in the endpoint. Okay, now that I gave a brief introduction on that, before passing to the results sections, I would like to give a brief introduction on multi-agent systems. So, as you might know, large-scale systems try to be implemented in a distributed way in order to improve scalability on them. And that's where the distributed algorithms appear. So a distributed algorithm is just an algorithm that tries to solve a global problem, but just designing the behavior of each individual system so that it only has to work with its own information and that of the neighboring agents. In the control framework, some famous distributed algorithms are average control, average consensus, leader following consensus, distributed observers, formation problems, etc. In order to define a multi-agent system, apart from the dynamics of each agent, one must take into account the communication graph. So, a communication graph is a mathematical object which tries to represent the connection between the network. A mathematical graph is composed by the vertices, which represent each of the agents, the edges that represent the relation within each of the agents, and optionally a weight matrix that tries to assign a weight to each of the communication edges. Then, starting from there, we can classify a graph being directed or undirected, depending on the symmetry of the communication lines. That is, a directed graph may have only defined the communication like in one way, while in the undirected case, if an agent I is connected to agent G, it means that also agent G is connected to agent Y. Then also we can consider that, as I said, the weight matrix was optional. We consider the weighted and unweighted graphs. So some important notes on multi-agent systems or key notes are that the most important aspect or parameter of the multi-agent system is the Laplacian, which tells us if all the graph is connected, first of all, that is which is a necessary condition to carry on most of the distributed algorithms like consensus or formation, and also tells us how fast the coupling dynamics of the system work. That is, how fast, if there is a consensus condition, will spread across the network. Finally, just a final remark that given the graph definition and the dynamics, one can classify a whole multi-agent system between homogeneous, when LD agents have the same dynamics, and heterogeneous, if each agent has its own dynamics. And it can vary as just having different value of the parameters or even having different number of states. Okay, now that I have given an overview of multi-agent systems and the cyber attacks, let me pass to the final section in which I'll explain the result of our work. Well, the problem we formulated for our work is that we wanted to implement a method to preserve consensus in a system while keeping the data being transmitted between agents secure. So, for this problem, we considered a homogeneous multi-agent system with nonlinear affine dynamics. That is, with nonlinear state dynamics, but with input and output relation. Most of the work that has been done on secure consensus has been done on a linear system, but here we try to extend it to the nonlinear framework. So, as a first step, we consider nonlinear state dynamics. Then, by the other hand, we consider a linear consensus law, that is a control law that is dependent on the error between the outputs of the neighboring agents and each agent. And we also consider that the proposed target plan cannot really reach consensus. Then, another condition we impose on the plans is that such plans are incrementally passive. We consider this so that, as we'll explain later, we want our protocol to be modular. That is, then we don't have to modify the dynamics. And with the passivity property, we can ensure that with a well-designed interconnection between the additional systems that we will implement and an additional plan, we can still achieve stability of the system. Then also, although this is direct, we consider that the graph is connected and also undirected. But well, as we said before, as we consider that the system already reached consensus, the graph assumption goes direct. Then, from the point of view of the attacker, we consider that the attacker can access an arbitrary communication line and can synchronize with the network if the data that they receive is correct. So, apart from that, we wanted our solution to follow these 4 guidelines. The first is consensus, as we said. We want that the system, as we apply our method, it can still get consensus. We also want modularity. That's the reason that we use the passivity property. And that is that we don't have to modify the nonlinear dynamics or the input-output matrices. Then we also don't want that to use additional communication channels for our method, as other methods propose in the literature. And we also want not to require synchronicity. That is, we don't want that each of the agents need to be synchronized externally. We want that our method doesn't need an external synchronization source, as it can be also dangerous for the security of the system. Well, not only the security, but also the performance of the system. So, our proposed solution is based on a previous work of our group, where we applied this method that we'll explain later to an estimation scheme. Our method, basically, what tries to do is to create an augmented output measurement function, which can still be differentially detectable. That is, that we can still recover the data once we get one endpoint to another, but we want to make it as complex as possible that without the knowledge of such model, an attacker cannot estimate the real data. So, why did we choose watermarking, or what are the advantages of watermarking? As I explained before in the review of the existing methods, comparing to homomorphic encryption, despite HE is more strongly robust, in real-time scenarios it can be critical because it may apply a large delay in the system. Then, comparing to differential privacy, in this case we can exactly remove the masking signal. And in comparison to moving target defense, here our method is way easier to prove stability and performance than in moving target defense, because then you have to consider an hybrid system with many output function, and also you don't need the synchronization of every endpoint, because in that case you will need that all the systems know at each time which is the actual output function of the other agent. So watermarking will be the first option, despite not being the most cryptographically strong. So here's a scheme of the proposed solution, and that will go as that. We would put the masking generator at the output of each agent so that the transmitted signal on the network is encrypted. And then at the input of each agent would include a filter that can filter out each of the masking signals received from each of the neighbors of the agent, so that the control law remains the same and we can preserve consensus. As you can see, the internal dynamics of the generators are linear. In fact, they are oscillators, but then we will have a nonlinear output function that would try to split the spectrum of the signal in order to make it more hard to decipher. We will not go in this presentation more in depth in the design of gamma, but in brief, we only need for it to accomplish some bounded derivative conditions. Then, in order to make our system work, we assume an additional assumption, and that is that the extended system, that is the system composed of the original dynamics of the system and the extended demasking filter dynamics, can still be differentially detectable. With that property, we can ensure that if we reach the consensus of the new output, we're going to still reach the consensus of the previous state, which is composed of the system state, of the original state, and the masking state. With that property, reaching a state consensus of the original system, we can reach output consensus. Then, from such assumptions, we get the main theorem of the work, the main result, which is theorem 1, in which, considering the previous system and the holding of the previous assumption stated, we can ensure that the original system can still reach a state consensus despite the addition of the masking. Then, in order to test our work, we propose an application case where we consider the network of 10 agents and an attacker. We consider a nonlinear oscillator with the following dynamics and an output function with the linear output function with additional noise. Then we consider that the attacker can connect to the agent 1 and receive its information and can bypass its information to agent 3. But the goal is that it can synchronize with the network without being noticed. So the masking protocol is defined as follows, as we stated before, and we designed it with the following structure. Each of the agents having 3 frequencies with different KIs for each agent and a nonlinear output function. Then here would be the obtained results. On the left, you can see a comparison between the behavior of the system with and without the masking protocol. On the top, we can see that the system can indeed reach consensus and can also reach it, as you see in the bottom, with the masking protocol. You can see that the final value is different because average consensus bases its final value on the average of the initial states. So as now we are working with an extended state, the final value might be different, but if, for example, we try to apply this to a leader-follower consensus where we have a reference signal, it would generate no problem. Then, on the other hand, we have the case in which the eavesdropper tries to access the network. In the top, we can see that without the presence of the masking protocol, the eavesdropper, as soon as it connects to the system, it can synchronize and reach consensus. While if we apply our method, it has very serious difficulties on trying to reach consensus and has a very bad performance. So as conclusions, as we said, the masking signal can prevent the spy from maintaining the consensus value. Then the estimation error, it has not been very well shown in the graphics, but it's only depending on the noise in the sensing. And finally, as I commented, the final value in the average consensus can be affected, but if we try to apply an external reference, we can overcome this problem. Then, in future lines of research, we will try to implement this method in discrete time systems. Also, we would like to try to find more conditions or more flexibility on the gamma function in order to make it more hard to decipher. We would also try to extend it to other distributed control schemes, also validate it experimentally. And as we are doing currently, we would like to try to extend this also to the data-driven framework, where we don't need the knowledge of the model and we can make some interesting advances. So finally, just to remind you, this work has been done in the framework of the Hora project funded by the European Union. So that would be all, and thank you all for coming.
Okay, I don't know if there is some questions in the room for Paul. Okay, so if there is no questions for Paul, I think that we can finish here these seminars. So thank you very much all for attending, and I hope that you understood what we have contributed with this project, and maybe you're getting some ideas on how to continue the research. Thank you very much, all.
Thanks.
Thank you so much.